Hello, hello, hello. No, you show me. Hello, hello.
Figure out कि यहाँ पे जो PowerPoint पे notes है ना, notes वहाँ डालो. That would be nice, right? If you got the notes to be there and this. Would you be also able to share the video that you're sending out, the link for the video? Would you be able to share that with me? और सर आप लोग तो थक गए होंगे. आप लोग तो थक रहे होंगे. नहीं, 2 दिन में नहीं हुआ. क्या बात कर रहे हो? I'll go ahead and share this. I'll give you this version here. This is, you can zoom in, everything is available. Nothing changes. It's still full. Is that okay? I'll say this one. Full. This is for both, and I'll give it to you for sharing out. Is that okay? Check, check. Check, check. Mic check. Working? Is it working? Yes. Yes. Life size, huh? Oh. ठीक है ना?
Screen, which is very small.
Okay. I mean, does it matter? I mean, that screen should not matter, right? Or
You will be there in the same room. You will look at that and see.
oh, I see. Oh, I see. Oh, I see. No, I can see from the distance. I mean, I can even see that now. So,
Yeah, whatever slides you are sharing, that will be
right.
and you as a speaker, that will be
Right. So that's the one, right? I can see
very
myself.
small, but it will-
Oh, I see this triple screen here. Okay, I see. You should be able to zoom out, just full screen there, right? नहीं वही आपको drag करना पड़ेगा नीचे से. अब वो वाला, हाँ. There you go. That is more than plenty. Life size of me is too much. It's hard to see yourself talking, right? I will save. No, but this is pretty. I realize it's like 2 seconds after I say something, that screen also says something. So it's always, you had to stop looking at it at some point.
This one. Now,
All set? Okay. Are we good? Can I go ahead? Can I start? Okay. Excellent. All right, everybody, welcome back. Oh, that's quiet. Good to have you all here. We have been talking about a lot of electric motors, a lot of structural. Today is multi-physics, which means we are covering, we covered structural, we went into thermal, and next we are talking about NVH, noise, vibration, and harshness. So this might be perhaps one of those topics where, as electrical engineers, like I said, I keep making a point that we often tend to ignore. That's not to signify a lack of awareness. It's mostly that we sometimes get intimidated by the amount of mathematics that comes with it. And that's not unheard of. However, I'm just trying to make sure I emphasize on the fact that it is important for machine designers, motor drive specialists, specifically to talk about these multi-physics phenomena. You don't need to have an expertise in every single domain. However, you do need to have a good understanding of how your design process goes through. So if I just start off with what we are looking at here, NVH is noise, vibration, harshness. You might have heard of it before. You might have come across this in your design courses. But NVH basically is evaluated in terms of different components, right? We have a full vehicle typically that you'll be looking at, every system that operates at its own natural frequency. So the way you start getting acoustic noise is when you have, I mean, like anything else, when you have two frequencies that match, they create resonance. I mean, like you might have remembered the prong, what's that called, the tuning fork experiments we have done way back in high school. We have a thing of water, one of those big water tubes, you can have different heights. Same idea. You're basically trying to figure out what frequency your system will resonate. So you can look at specifically from the perspective of mode shapes, isolating buzzes, squawks, rattles. A lot of these things can actually happen, but not all of those things will happen for motors. But for vehicles, it can. You have aerodynamic noise, you have mechanical noise, and of course, the one we really care about and you recognize as a very important component is electrical. That component comes in from your design itself. If you have acoustic noise generating from torque ripple, from electrical noise, it comes from your system. So in terms of the application of acoustics, acoustics really is the study of the generation, propagation, absorption, and reflection, which basically what that means is that you are talking about applications like sonar, you're talking about concert halls, machine shops, automobiles, ultrasonics, underwater acoustics, geophysical explorations. All of those really dig deep into the idea of acoustics. Now, you separate that from the idea of sound, where you actually define noise as something that's undesirable or disagreeable. So we don't always refer to everything as noise, right? Some things are sound, some things are noise. The fan operating, you might not consider noise. You might consider that to be sound because that is an acceptable and agreeable sound to you. If it were to whine and groan, or if it was if you have ever gone in a car and you consider that to be like there's a coin somewhere that's stuck and it's rattling, you might define it as noise, not because it's loud, but because it bothers you. So the same way as well, if you think about frequencies, one of the examples that I've always heard people talk about is when you have a child, oftentimes for a parent, if you have a kid or if you know the kid that you're related to, oftentimes you'll see that at night, if you're sleeping, you can still hear certain sounds. You can actually hear the child as they are crying or as they are calling out from a distance. Partly, once again, this is mostly anecdotal because being a parent and people around me you can recognize your child's voice from a distance because you tune. There is a tuning that happens, whether it's natural or just experiential. It does connect. So it does not bother you. Instead, it resonates with you and creates that awareness. So sound, if you define it, it's basically just pressure, right? It's waves. So you're talking about pressure variations, oscillations, which happen in a medium. It could be air, water, solids, no matter where it is. That's where you're defining the idea of sound. It goes in the form of longitudinal waves, and it basically has a bunch of compressions. Basically, it has compressions and rarefactions that actually happen in a medium that tends to be elastic. So when your sound propagates, the oscillation pressures basically go above and below the mean pressure. That's essentially how you hear different sounds. Now, what does it come down? How does it relate to acoustic variables? So as your sound propagates through the air, it basically causes a real change in essentially or a fluctuation in your pressure, in the velocity and everything else. That's how we hear. If you think about it, even if you look at fireworks, you can see it before you can hear it. Light travels faster than sound, simple as that. So you can see it, and then about a couple of seconds later, it snaps. The same thing, lightning. You see the lightning before you can hear it. Because when you see the lightning, you know it's going to snap in about 2 or 3 seconds. That's because it's not because it didn't happen at the same time. It's just because light just travels to you a lot faster than sound did. And that's why it's that method of a collapsing field that can create noise. If you have a discharge, a partial discharge, ionization, all of those create noises that you are automatically tuned to. For generally speaking, in terms of acoustics and noise control, your idea of looking at a fluctuating portion is an important concept. So if you look at the idea of the pressure, velocity, and temperature, it just tells you how you calculate each one of these variables and what the units are. So sound is basically, like I said, generally speaking, they have 2 different options for your waves that you're talking about. You have shear wave, and you have longitudinal waves. Longitudinal waves basically are the compressional. They are basically compression type waves, and shear waves basically is a propagation type. So it's a particle motion. So it tends to be orthogonal to the direction in which your disturbance is happening. So that's the 2 core mechanisms that you will see sound moving. If you talk about the speed of sound, you can calculate the speed at which sound is going to move as a function of bulk modulus. You might remember equations from elasticity that you have looked at perhaps back in the day. Then you have shear modulus, and then you have density of the material. So it does matter where you are trying to evaluate or where you are looking at the presence of sound. Like, what is the material? If you have dense air, or if you have water which has a colloid in it, all of that changes how that noise propagates. So in terms of acoustics, you know the definition of wavelength. We always talk about it, right? Wavelength is given as lambda. It is C over F. And it is also given as 2 pi over K. So when you talk about the pressure, you have a function of wavelength connecting to the period. In terms of units, we will refer to some of these units later in the session today. We are typically, you probably remember from high school as well, when we talk about sound, we have a frequency for which we are mostly sensitive that clocks out at about 10,000 hertz, right? 10 kilohertz. So 10 hertz to 10 kilohertz roughly is where we talk about being most sensitive. Or is it? No, 20 hertz, 20 kilohertz. And your increase in 1 dB essentially is the minimum increment that is defined as the necessary increase for it to be noticeable. Beyond anything less than that in decimals, we don't consider that to be very noticeable. One of the things you will notice is that there actually are several studies that define and qualify what noise, what levels of noise is acceptable. I mean, 60 decibel, I mean, normally I speak louder. I tend to project my voice a lot more. So I would be much higher. I would imagine I'm somewhere to the tune of 75 to 80 decibels when I'm talking. But once again, you have to have an actual decibel meter to figure out how loud anything is going to be. You can buy a simple multimeter attachment that can also tell, or your oscilloscope attachment that can tell you what level of noise you are getting. You don't have to have a very complicated DAC system, although for motors, it is always advisable to have something that's like National Instruments has this full setup that you can get that actually can measure NVH, that can specifically measure acoustic noise and other units. sound intensity level and the sound pressure levels, you have simple equations that can be used to calculate. So if you know what the RMS pressure is and what the reference pressure is, you can calculate what the intensity and loudness of your noise is going to be. So in terms of numbers, like I said, here are some basic numbers. I use this information just to kind of give you a reference for what you might think is acceptable. For some people, they can tune out the noise of an airplane because they live right next to the airport, and you just get attuned to that idea of having that background noise, and you learn how to naturally filter some of those noises out. For some of us, we've grown up in a family in which you might have had a lot of kids, so you can isolate yourself from noise very easily. As a matter of fact, right now, one of the studies that we are currently working on, and that's not related to motors, specifically is looking at ideas like what COVID kind of created, where people have gotten used to working in an environment that's at home, which is very different from what you have been used to doing before that. So the types of noise you have been used to isolating might be different from the ones that perhaps you are at this point looking to isolate. So previously you would be looking at students talking, there was a murmur, but there was no doorbell ringing. You might have people who are talking outside your office, but there was no child who walked in the back and asked you a question or started playing a TV show right next to you. So the types of noise has changed, which means what's considered to be tolerable has also changed to quite an extent. You might be okay with the quiet hum of an AC, but a rickety fan that makes noise might not be okay for you. So that really depends. So and this is definition. So everything, if you look at it, wrinkled newspaper is considered to be 70 decibels. So that's not necessarily quiet. And you can imagine if you go to a movie theater, if somebody pulls out a bag of candy or something, it is a lot more annoying there than it is if they were doing this, well, in a classroom, it would be just as annoying for the instructor. But for everybody else, you might not care, right? So you have to define for your given application. The reason I say all this is because if you're talking about NVH for motors, it depends. For example, if you're placing a unit for HVAC on the roof, in that case, acoustic noise might not be quite as bad of a problem. But if you're trying to put that inside a building, well, let's say you're putting it for a centralized AC unit, now it is a problem. If you're trying to put the AC for a data center, where nobody's really going to sit and it makes a little noise, it's acceptable. But you do the same thing inside a gymnasium, now you have a problem. So the definition is oftentimes contextual depending on where you're putting it. But as a general rule of thumb, we try to always keep NVH at its lowest possible number. The reason why oftentimes we get away with it is because, like I said, we are trying to optimize for a different variable, and acoustic noise being a side effect of that, we sometimes tend to ignore. So, like I said, I was 10 hertz. I was strong almost entirely with my frequency range. The most sensitive frequency range is 500 to 8 kilohertz. But normally, if I remember correctly, our audible range is 20 hertz to 20 kilohertz. That's what number we grew up hearing all of our life. But the sensitive frequencies are between 500 to 8 kilohertz. And the frequency weighting that's used for sound meter basically are in response to human ear, which means depending on how you feel, how you hear sound, you might nails on chalkboard. That's something that everybody talks about. We talk about how nasty it is, but not everybody is bothered by nails on chalkboard as much as some people are, right? So there is a context. It's like smells that you really cannot know what smells foul to somebody and what doesn't. So the same thing that we use, the most common weighting that is used is what's called an A-weighted measurement. So A-weighting essentially is, it's like the ear. It cuts off the lower and higher frequencies that the average people cannot hear. So it basically gives you an A-weighted value for all the noise that you are going to get. So there are a couple of kinds of analyses that we use mostly. There's modal analysis, there's harmonic response analysis. There's also the time domain analysis. It's used quite regularly. The first two are perhaps more widely prevalent when it comes to electric motors. And these analyses can be solved as either as purely acoustic problems, or you can consider them to be vibroacoustics problems. Can anybody here tell me what vibroacoustics are? I mean, like generally speaking, you know what they are. It is the acoustics created because of vibration. Exactly. So there's no complicated process there. So when you're talking about the idea of a coupled acoustic model, something that to take into consideration, like I said before, is that they're both interrelated, which means change in your frequencies can lead to a change in vibration, can lead to a change in your acoustics you hear, right? So this is essentially a coupled problem. Once again, if you define acoustics solely on what you're measuring from your unit, you might not be solving the problem. Because if you want to only solve the problem of acoustic noise, you can put a jacket around it. But if you want to have a solution like, let's say, what Bose does, right, the headphones. If you have noise canceling headphones, you have some headphones that cancel specific frequencies, which means if you're sitting on an airplane, it will take out the noise of the airplane. It will take out the noise of a bus you're sitting in. But if somebody talks to you, you can hear them, right? It clips very specific frequencies. Alternately, if you buy, I shouldn't say cheaper, but if you buy a little less specific headphones, when you're sitting and you talk to somebody, they simply cannot hear a word of what you're saying, because it muffles every single sound coming out of it. So the question you have to at some point address for your application is, which kind of a solution are you designing for? So there are several app options. We have done some projects, and we're actually in the process of looking at some patents specifically in this space as well. So I'll refrain from talking about that. But generally speaking, it's a very interesting area. So modal frequencies, we know what this is, or at least you've heard about this at some point. The idea of modal frequency is that every material has its own natural frequency. You've probably seen it in movies, possibly even seen a demonstration when somebody puts a champagne glass or a window or something, a certain kind of noise is sent out, and that creates that resonance with the material and causes the glass to shatter, right? That's not because of a physical wave, but I guess in a matter of speaking, it is because you are sending out the specific frequency that resonates with the natural frequency of that specific material. So the external force of excitation creates a vibration force that then causes a forced vibration, and those frequencies, basically the excitation frequencies, they collide with some of the other frequencies, create basically an addition subtraction of the oscillations, and that mechanical resonant essentially are your resonant frequencies. So if you look at specific patterns of vibration, in that case, what you get from a very specific pattern of vibration are referred to as modal shapes. So if you have done NVH analysis, let's say on a software like ANSYS or COMSOL or something, you might realize that they have these modes where they show you the shapes of deformation that you get in an electric motor, right? So the idea basically is, and it's not, deformation is not that the machine is actually shaping out into an egg. These are much smaller deformations that create that vibration. So you're more interested in the vibration and acoustic noise it creates, because it's not necessarily to identify whether your shape is going to turn into an egg. It's not like a ball or tennis ball that actually changes its shape very, very visibly. So, so the program assumes essentially that when you're talking about this, the system assumes that your, like I said, is incompressible, right? So if it's incompressible, in that case, very small pressures can actually be moved. So this is actually just to give you an idea of modal analysis. This was in 1940. Tacoma Narrows suspension bridge, it collapsed because of wind-induced vibration. Basically, it gave them flutters, and it actually, the entire building collapsed. So that definitely can happen, and it's not very typical. Obviously, we don't hear about it all the time, but it is something that the higher the tower, for example, you still have to think about everything from oscillation all the way down to the acoustics is going to be exposed to. So modal analysis, like I said, is the study of dynamic properties of linear structures. It is based on oftentimes it uses FE solutions. When you talk about the dynamic properties, you are talking about natural frequencies and also about eigenfrequencies. And then you also have modes associated with it. These are called eigenmodes. The dynamic properties, they depend on several variables. You have mass, you have stiffness, you have damping distribution of the structure. Basically, you are talking about how stiff and how elastic, or how elastic your defined system truly is. And that creates an opportunity for you to understand the structural response in terms of its natural modes and frequencies. So like I said, in terms of the source of noise, this did not come out properly. So we're going to refer to magnetic radial forces, torque ripple, and natural frequencies as sources specifically for motors. So what are the different sources of noise? Like I said before, you can have the first one essentially is between the 0 to 1000 hertz. We are mostly interested in that. Anything above variation that you get oftentimes can be in 3 categories: electromagnetic, mechanical, aerodynamic. Simple enough, not very complicated. The electromagnetic noise comes from the noise affected oftentimes from parasitics. You can get it from space harmonics and also from eccentricity. So if you have a phase unbalanced, you have one of the phases going out, you have eccentricity in your bearings, you have the shaft that gets deformed. All of that can cause you to have a rumble, a groan, a drone, you name it, it can be something of that nature that you define. It essentially what it's doing is it's causing a magnetorestrictive expansion of the core lamination. When that happens, the air waves essentially move. It creates compression and decompression, and that causes those noise to be, or the sound to be propagated. Mechanical noise, like I said, specifically that ones that oftentimes we tend to hear are the ones from bearings. So those are very typically mechanical, coming from the motor. You could have other, for example, coupling noise that you might get if you are coupling it to your load. That could also be mechanical. Aerodynamic essentially is if you have a system in which you have flow of ventilating air over the motor, whenever there is a motion that where you have the body cutting through air, you can end up with a situation where you can get aerodynamic noise. Depending on how it is, like I said, the frequencies can be high or low. It can be something like a swoosh or almost close to a whistle, as you might hear. In some cases, vibration-induced noises can actually be loud enough to cause a very high frequency whine that can really catch you at the wrong frequency. So load-induced sources really, there's a couple of points to consider here. First, the noise because of the coupling, like I said, you can have that because of shaft misalignment. You can have belt transmission, elevator sheaves with ropes. You can have tooth gears, coupling, reciprocating compressor. All of these can lead to sounds that you can hear. Mechanical sound. You can also have an issue with the mounting. If you have ever looked at a car and you have an alternator or something and you have a motor mount that's off, you mount it and there is a vibration and the motor adds to that vibration. Now you will get additional noise that comes from your system. It can be a function of wearing out of your bearings. So your bolts, the bolts that you have attached. In some cases, it might just be as simple as your motion or the vibration in the overall body was substantial enough to where your bolts were not accurately sized. You have to have the thickness of the bolt, the diameter of the bolt has to be right to make sure you don't end up causing them to wear out sooner than normal, right? So think about it, if you're talking about a wind turbine sitting in the middle of the offshore wind turbine sitting away from the shore, you're going to get a lot more wind there by definition. That's why you put the wind turbine there. But that would mean you're also going to get a lot of lateral motion that comes with that turbine. So which means you have to make sure that your mounting assembly is done right. So the noise that you get from the source is transmitted through some medium, and it goes to the recipient. It could be the recipient, could be a human, it could be another system, another subsystem that you are essentially exposing it to noise. The ones we care about really are magnetic. We oftentimes look at noise, and the part that we as engineers are looking at is magnetic noise. The stator frame that you have is primarily the radiator of the machine noise. And if your frequency of the force basically is close to any natural frequency, you will hear that happen. You can get system deformation. You can also have parasitic noise that comes from your higher harmonic frequencies, right? You have a power electronics, you have a frequency that basically go much higher, you might be able to hear them. In addition, as also you can get torques. It actually creates ripple, or it basically creates parasitic values in terms of the acoustics that it generates. And one of the important ones is the voltage ripple in the rectifier, which itself can have its own kind of an oscillating torque that is directly audible, or basically can directly be felt by the user. So in terms of, like I said, in terms of the different sources, we have bearings and defects, you have ovality, you have sliding contacts. And of course, our goal here is always that we want to have it as closely balanced as possible, right? We're trying to make sure our system is properly balanced. We're trying to avoid eccentricity. The way we are talking about eccentricity is not just about looking at the quality of the bearings, which is a very important part, but we also have to have ways to do fault prognostics. Because you need to know when the fault is happening rather than after the fault has already happened. When we talk about permanent magnetic machines, I will talk to you guys about, that's tomorrow, I'll talk to you a little bit about one of the methods we implemented using surge coils. And you will see the idea was to identify the fault or the failure as it is happening instead of waiting once the sensor is gone, once the system actually is in jeopardy. You can also have noise due to rolling bearings, and you can have them in terms of the sleeve bearings have a different kind of noise. These noises are identified by the type of frequency and the intensity of the sound that they produce. So the most basic definition that we all understand, case in point being in this room, is the aerodynamic nature of the fan. But if you put that behind the motor, you will still have that aerodynamic noise that comes from the back, because you have a fan mounted on the back of several motors. It causes air to flow through the motor. So anything that you have along its way is going to create some noise, right? So that means if you have a non-sealed motor, the noise, the internal fan comes out from the vent holes. Now it would essentially, if you think about it, it's like a flute. I mean, you are essentially trying to control the different orifices that are available, and or not so much in that case you're trying to control. In this case, depending on where it comes out from, your frequency might actually be a function depending on how much venting it has. Based on spectral distribution, there is a noise base, like I said, 100 to 10,000 hertz, a siren noise, which is a tonal noise. So if you want to eliminate the siren noise, you can increase the distance between what you have, what you call the impeller, that's the rotating body, and the actually stationary obstacle. If you go further, the noise goes down. But other than that, it's a very mechanical noise. So in terms of the noise prediction methods, if you want to determine noise, you have a couple of options. One is deterministic, one is statistical. The idea is very simple, right? Deterministic basically means use FEA, do a structural model, create an acoustic model, calculate sound pressure. Very linear, very methodical. You can see exactly how that happens, right? On the other hand, here, you take it one step further. You also add a component of radiation efficiency model. We're not going to go into much details because our idea here is not to kind of go super deep into NVH as a science. We are trying to look at NVH as it applies to electric motors. So in terms of the accuracy, the biggest challenge oftentimes for NVH calculation really tends to be the calibration of noise, because you are determining your natural frequencies based on the motor that you have designed. Now the challenge here is if you set the wrong boundary conditions, right? If you tether the wrong point, because when you look at the motor, it makes a certain noise. If it has a noise where it's able to move about its source, the foot, if you make it a face mount while you're simulating, if you simulate a face mount while you have actually put together a foot mount, your acoustic signatures are going to be off because your housing relies on your ability to tell the simulation what parts of the motor are actually connected. So this can be a little challenging, and the most practical approach is to use FEM, so finite element methods. The idea of FEA basically is that you would use the matrix for mass and also for stiffness. Those are the two variables that we consider for NVH analysis. Now, when you talk about the physical properties of the materials that you're using in the machines, you don't always know what the stiffness level is because you only have the material properties as the manufacturer provided to you. So whatever numbers they gave you, if they ran the test for it, you have access to it. But without that information, you are essentially going with data sheets of materials that are closest in match to what is currently available. So there are aspects of anisotropy in laminations and anisotropy, and that basically can lead to internal stresses that are caused in manufacturing that directly lead to a change in the stiffness matrix, and you're talking about Young's modulus and such, stiffness matrix K, because you have a temperature variation, which means, once again, keep in mind, things become metal more malleable when you go to higher temperature, right? Which basically means they bend easier. That's basically how we change any shape of anything. We increase the temperature, which means if the temperature inside your subsystem is changing, then the stiffness of your system is changing along with it, which is something you need to take into consideration if you want to know the true modes of operation. Once again, that means your NVH behavior is now getting coupled to your thermal behavior. If you are going to go at 100, 150, 100 to 120 degrees Celsius, the question is, are your NVH models aligned and in line with what you're trying to do for high frequency or high temperature solutions? The idea of damping matrix C, which is difficult because it's a mechanical function. We are trying to define, if you remember damping function, it would be something like a spring motion, right? You're talking about something that slows down the motion. It's a material property. We have a difficult time. We can only trust what FEA is doing because that's usually, unless you go experimental and calculate the real numbers, it can be difficult to predict that matrix C. And oftentimes you don't see very many perfect models, if any. So that means your force vector, you have to identify them as at as many points as possible, so that you get a very good or effective description of your acoustic behavior. And you have essentially you use 2D FEM that allows you to calculate analytically the forces that you're generating. I will show you a couple of options that so one thing to remember, like I said, is no matter what you do, at the end of the day, analytical methods and FEA can only be so effective. Which what it takes you to is basically you have to run lab tests. Now that creates a whole nother of I shouldn't say challenges, but it's because if you want to measure acoustic noise, you have to know what the ambient is. For example, we were doing some tests for one of the motors, and the frequency we were finding was actually coming from one of the power supplies. So we had a DC power supply, 300-volt power supply connected to my motor. The motor was giving us certain noises, but the power supply was giving us a lot of it as well. So we had, I don't want to name the brand, but we had a specific power supply that had a fan going inside it as well, and it had a whine. So in some cases, you might hear the hum of a transformer that you have inside, and you can hear that as well. And that frequency can be very close to the frequency you are getting from your motor. So now you might end up getting frequencies that are not real, because when you go to the field, you won't have a power supply. You are going to use either an embedded inverter, or you're going to have an inverter that's tied from somewhere else. In cases like that, there is a significant value in having access to an anechoic chamber. I don't know if any of you guys has anybody here seen or been in an anechoic chamber? Do you guys have one? Yeah. You have an anechoic chamber at university? Yeah. That's fantastic. Vehicle horns. Wonderful. And your university has that on campus? Where I study, they have it. That is wonderful. So anechoic chamber actually is not a resource. There's two things oftentimes for transportation research that are difficult, actually three things that are very difficult to find in my opinion. One is an anechoic chamber. That's perhaps the biggest, that's the one that I normally don't see in most places. Second is a battery abuse testing facility, because that by definition has a lot of challenges. The third thing is a wind tunnel. So wind tunnel basically is for identifying, once again, you're looking at the frame of the vehicle. You're trying to identify how much noise you're going to generate, what kind of drag you're going to get. That's for the vehicle. So wind tunnels can be hard. The fourth thing I haven't mentioned, which perhaps is important, but several universities do have it, but not all, would be a chassis dyno, a place in which you can actually put the vehicle and do all of your vehicle testing and benchmarking, right? So these four things in transportation research, having them accessible does, in my mind, in my opinion, give you a substantial benefit or edge in doing your research. So, well, I'm well past my time. Okay. So, like I said, we just started a little later, so we didn't start at 2 exactly. Okay. So, in terms of noise prediction here, we have Cogging torque, we have the distortion. We normally apply sinusoidal, right? We want to apply sinusoidal waveforms. When you apply a trap waveform, a trapezoidal waveform, by definition, you're introducing harmonic, right? It's anything that's not a sine is basically is noise. Anything above the fundamental frequency is considered to be noise, which means for a trapezoidal waveform for a BLDC, you are going to get noise from it. And this basically can also have in terms of torque ripple, you can also get that from the difference in parameters for the air gap in terms of your D and QX measurements. The cogging effect that you get from these variations can cause what is called cogging torque. And the higher harmonic that you get from the magnetic flux density is called the field harmonic electromagnetic torque. Okay, so if you talk about the sources of torque pulsation, once again, we go back to the same issues. We have the cogging force or the cogging torque. You have distortion. You have difference. Oh, that's actually same slide that got changed somehow. So in terms of minimizing the torque ripple, you can minimize it primarily of our interest is minimizing it in terms of the motor design and control, which that's where we normally start. Okay, and then you have measures taken to minimize would include things like elimination of slots. You skew the slots. For PM machines in particular, you will see induction in mainly you'll see the copper bars are never straight, right? They're always at an angle. They're done also to reduce the torque ripple. For permanent magnets, oftentimes you will see that they also talk about skewing the rotor. So in terms of skew, there is real value in doing that. You can have special shaped slots and state laminations that are specifically designed to allow you to essentially what you're doing is you're trying to figure out what your resonant frequency is, and you're trying to change the design or the structure so that you don't hit them. So it's not a black box approach. You are trying to be very strategic in how you are going to make this not be noisy. If you know what frequencies are going to be most problematic, eliminate those. You don't have to eliminate all of them, because that's not, I mean, once again, that's my opinion. In some arguments or in some cases, you might see that the requirement is to remove. In my mind, you are talking about the most dominant frequencies, and those are the ones you're trying to knock out. You can also have shifted magnet segments, in which you basically, as you go along the axis, you stagger them a little bit, essentially creating the same idea as skewing. You can have direction dependent magnetization of permanent magnets, and of course you have control techniques. We always have control techniques for reducing torque ripple in motors. You can have options like slotless machines. If you do slotless machines, you basically you are trying to increase the air gap, which can then reduce your PM effect. So like I said before as well, whenever you're trying to design a machine, you're trying to get all the field to go from the stator to the rotor and vice versa. Whenever you have to increase the air gap, you get some benefits in a vehicle system or otherwise. But whenever there's more gap, by definition, you're going to have more losses. So that's really how that works. So you can look at making the design have a wider air gap, but you will end up with some challenges. Skewing of the stator slots, normally you do the stator slot skew by one slot pitch. That allows you to reduce the cogging torque practically to a value of 0. But keep in mind that the stator is not exposed to the rotational forces, the rotors. So your optimal skew oftentimes can be less than one pole pitch. So if you're talking about it, essentially are inserting converting the laminations, instead of stacking them along the z-axis, you stagger them as you stack them. So they come out. So challenge exists here in your manufacturing. So you have to find a good way, because if you remember how we talked about specifically creating mechanisms for stacking them. So now if you want to skew them, you might possibly be looking at creating notches that are staggered. Here's the challenge of whenever you have anything that's staggered. Can anybody tell me what that challenge could be? What is the one possible issue with having laminations that are staggered, or essentially where your let's say your notch is from the, let's say, moving all the way from the right to left? This one is electromagnetically, you have to make sure you are in the right place. Second is your laminations are not going to be identical, which now creates a question of, is it possible to basically stamp them out? Can you get the same lamination at a reasonable cost? If it was all laser cut, easy enough, or reasonably easy enough, right? So you cannot just skew them because you want to. There are manufacturing challenges you do have to consider and you have to overcome. So if you're looking at minimizing the ripple, this actually is a book by Jesse Giras, who has a specific book on vibration and acoustic noise for electric motors. So it's actually called noise and polyphase motors. Yeah. So you can do the stator slot shaping. You can actually shape it to a place where, if you remember field reconstruction that I had talked about before, that was one of the objectives, is that we would look at the field distribution inside the machine and start changing the BN and BT, because what's happening is that acoustic noise basically goes into the slot, and that causes your motor to have a certain kind of noise. Has anybody here heard of a Helmholtz resonator? So Helmholtz resonator, basically it's like a ceramic beaker used for your experiments. Actually, you know what? It's just like a slot. It's got a shape that's very similar to a slot. It's got a neck and it's got a cavity. So it basically does the same job as defining, if you use the length of the neck and the size of the cavity defines what frequency you're going to clip. So ideas like that can actually be used to design what the system is. The challenge is, how do you find out what the optimal slot is? Because the process of electromagnetic forces, taking it all the way down to acoustics, is a very long process, because FEA is fundamentally very challenging. It just takes a lot of time. You can have bifurcated slots. When you have a closed slot, in that case, your bridge must be properly defined. So you see, every time we try to address one challenge, we are defining another one. So we say we're going to design closed slots to reduce noise. We say you have to make sure that you have the right bridge design to either structural rigidity, or you might be looking specifically at magnetic behavior. If you have a narrow bridge, Now, magnetically, we talked about this morning, you'll get saturated. So now that's a hotspot creation. Now what? Right? So if you have a closed slot, you can essentially have sold slots which are much closer. So there are different ways that you can approach the problem, but in any scenario, whenever you are going away from a standard design, the general requirement is going to be a corresponding influence on the thermal or the electromagnetic behavior. Just as an FYI, we will actually be flowing straight from this slide into the next one. So even if I'm going longer on this, we will catch up on the other one because it's one single piece. So you have shaping of permanent magnets, skewing of magnets, and then you have shifting of permanent magnets. You have the width, you have the magnetization, and then you have magnetic asymmetry. So as you can see, everything deals around change the shape, change the magnetic direction, and change the way you have placed them with respect to each other. So placement, shape, and orientation in some many ways, right? So we are trying to find every single stakeholder, every single component that might have sensitivity. You're trying to figure out how controllable truly is your system. If you're thinking about control systems, you have two options, right? You have controllability and observability. We are in this case talking about controllability. We're trying to figure out our most accessible variables that give us the most observable output. So that's the question that we're trying to address. So if you're talking about this, the question really is, in terms of discussion, how does vibration acoustic noise show up in traction application? What are the extended consequences of NVH issues in motors, and what approaches can be considered for acoustic noise? Should they primarily be electromagnetic, analytical, design-based, or passive? I call this brute force. It's anybody else would have considered it very offensive. I'm not meaning anything by it. I'm just saying passive, meaning it clips out, like I said, it muffles the noise. It takes out all noise. Or should it be a little more surgical, in which you are talking about specifically isolating the frequencies and only clipping them out? So I wanted to open this up for a quick couple of minutes to see what you had experienced, what you have seen in your own designs perhaps, and if you had any thoughts. Anybody have anything they want to add, share? Okay, so we'll have that question answer session at the end. At some point, I'm hoping that we can talk about this more, because like I said, I'm not necessarily just looking at this as something we have to do. I'm more looking at this as something that allows us to change the way motor design is done. So we're not just doing this because if we don't do it, the motor won't be right, but the way motor design has been done is not right. That's just my opinion. So if you take that from there, that takes you to the next side of conversation, which is closed form multiphysics design. Because you have established what we are trying to do. We established what the problems are. Now we need to figure out how we can actually create a framework. So like I said before, we are going back to what we're trying to do. Our question always is, what is the overall objective? I would never expect anybody to start a problem without knowing what the metrics for success are. How do you know you've been successful? I mean, it's like running a race but never knowing where the end is. You don't want to find that once you get there. You need to time it so that you get there with enough energy to spare, but not too much, right? Same with machine design. You need to make sure you're not overly complicating the process, because that could take too long. On the flip side, you need to make sure you have met the design considerations for the given applications. So now here's where I start to talk a little bit more in terms of specific numbers, and I'm going to have to look into my screen as well so I can read the numbers a little more carefully. So when you design the traction motor, there's few steps you have to consider. The first one, you start with the selection of your motor topology and the type. Why? Because a lot of times you will hear people talking about the fact that, well, I want to have induction motors because no permanent magnets, or I want to have PM because we have an artificial permanent magnet we make here, so we can easily get it, and we don't have any problems when it comes to noise. We are putting it in the middle of nowhere, so don't worry about that. So you can select which type of motor you're going to get based on your application. You have to look at sizing for thermal management, torque, and power capability. So basically designing objectives and constraints. So always start your machine design process with setting an expectation of what it is you are trying to do. If you go through a black box of design, the problem is you will never know when your motor actually was successful and if you met the requirements. The output power capability basically is you have to figure out how much. I think we had some of the people who said yesterday, you are trying to extend the constant power region because going to higher speeds allows you to reduce the torque requirement for the motor, right? If you think about what a hybrid electric vehicle does, when you go on the highway, your engine is basically cruising, or even a regular car. On the highway, your engine essentially is cruising. There is no change to your speed. You're not requiring a high torque at that point. The high torque regions are during startup, right? That's when you need the high torque. So by being able to go to much higher speeds, you can possibly make the motor much smaller. Calculation of operation requirements, you need to know what the initial acceleration needs to be. You need to know the gradability, cruising speed, and power requirement. Now you go back to the original slide we talked about yesterday, when we're talking about each one of these forces. Now those forces formulate, or kind of they make their way back into your motor design. Or so if you're trying to do the final design, and if you are, once again, there's a difference. Once you have the user experience, oftentimes you will see machine designers say like, I know what I'm doing. I don't need all of this because I have everything in my head. But having a method to that process always should ensure repeatability and reproducibility, because you cannot have a system that is very user centric. That's, once again, it's my perspective. You need to have a system that can be automated, because over the course of time, that's what's going to be needed, because we want to scale them up and down. Gone are the days when your motor could be made for a fan but used for a blender. No, different profiles. You cannot do that anymore, right? You cannot use a lawnmower engine to run a car. It just doesn't work, which I recognize a lawnmower might not have the right reference here. But generally speaking, if you're talking about a motor that comes from a motorcycle, cannot go into a four-wheeler, right? It just doesn't work. So after the type, you go into the multidimensional details, and the goal is to address specific rotor structures, stator structures, and identify what kind of multiphysics behavior you're going to see. So if you break that down in terms of a visual, the conventional multiphysics design flow tends to be something like this, right? So you're talking about a system level. The first level is the control inverter and motor type, and then you have level 2, which is a dimension loading design, and then level 3 is your electromagnetic, mechanical, and thermal design. So that's your linear flow. It's basically, it does feed up, but it only feeds up one level. You don't feed back up to the motor type and design selection. I'm not saying that is necessarily what is needed, but what I'm saying is this has been one of the multidisciplinary design optimization methods, where you're looking at every one of them simultaneously. This was a more linear method, which you can talk about in classic design. You're going from stage 1, which is template-based spreadsheets, stage 2 is electromagnetics, and then thermal, and then structural. And then it's iterative. If this doesn't work, go back. This doesn't work, go back. Doesn't work, go back. So you basically figure out what your entry point or what your recalculation point for your system is going to be. So you have multiple ways of tackling the same problem. And depending on the resources available, you might pick one of them. Optimization algorithms, we had a question this morning about specific methods that you can use for optimization. You have gradient-based algorithms or intelligent algorithms. You can have conjugate gradients, sequential quadratic, evolutionary, which is oftentimes genetic algorithm, is one that you can see. Evolutionary programming is one more. So these designs, basically what they do is you start with a specific design, and then you basically start to change them little by little. And you iteratively check to see, you keep everything else the same, and you only disturb one variable and see what the impact is. And based on that, you can either extrapolate the information and say, this is what's going to happen over the entire range, or you go into step by step and start combining them to create an idea like that. So this is basically what we have defined in terms of the integrated drive framework. What we set out to do really was to create a flexible and time-efficient model. We wanted to look at everything starting from drive cycles to multiphysics to current shaping control. I will talk about drive cycles tomorrow. Today, I'm only going to talk about the first two. Our drive cycles will be on day 5. We'll talk about them specifically, about how we do simultaneous coupled optimization. But the idea basically of the drive cycle is we need to integrate that with a clustering method. You have to do deep learning, create a large pool of data, identify where your motor is going to operate. You had to start there. And then you create a surrogate model, and then you optimize the entire system in one single piece. This is the overall framework that we have defined for our method. Now, we are trying to always, or in our case, we were trying to figure out what the geometry is going to look like. You start off, of course, with the machine geometry based on the controls that are provided to you. and you have geometry factors. Combine those two, you get the electromagnetic model. From that, you implement a surrogate model. That's just one that we considered. And then from there, you get the vibration level, you get the efficiency and torque ripple. The external feedback here is feed forward is drive cycle that gives you a cluster map of where your motor is going to be. For example, here you see we have 1, 2, 3, 4. I touched it. Thank you. Thank you. So, and from that, you create the representative points. I will talk about them, what they are tomorrow or on Friday. But that gives you the information you need for creating this overall design. So let's start with the vibration surrogate model, keeping in line. Yeah.
Should we consider dominant frequencies? Because here, because once again, it is when we are designing, if we have prior knowledge of dominant frequencies, we can predict about vibration.
Yes. So yeah.
By designing this framework,
yeah.
Do we need to input?
So yeah, so if you have prior knowledge of the vibration frequencies you're going to get, the question I would have is there need to design? Because if you are going to change the design, possibly we did not do this, but yes. So one of the things we were looking at was creating a drop-in replacement for motors, in which you have a motor, you know what the prior vibration frequency was for the given design, and now you are evolving that design along the way. In that scenario, I will actually show you specifically, we did multiple designs. So yes, it can have value. Whether it is directly usable, it would have to be a case-by-case analysis to see whether that directly happens or not. But yes, what we did actually was creating essentially an interpolation map of different design variations. And we're training the system to recognize what happens when, what happens if. And based on that, you can predict, now I have trained it for a certain number of points. After that number of points, the system can, even if you did not train it for a certain, like neural network system, even if it was not trained for that point, it can still tell you what the acoustic noise was. So yes, so there is value, but you have to be careful in how you are integrating that into your model. Along with the frequencies, you would also need to integrate that initial design for the motor. So that then has relevance. Having a frequency model that doesn't connect to the electromagnetic model then now has no meaning. That makes sense at all? Is that reasonable? Okay. So in vibration surrogate model, like I said, here is the frequency. So what we're talking about is you have the sources that mechanical vibration, aerodynamic noise, electromagnetic. We established that. I've said that a million times now, so we are good on that. Now, the vibration is basically a function of frequency of your radial forces, which means you can define the mechanical system as a lumped parameter model. So when you're talking about the overall system here, your stator and frame assembly that you have is given with your mass M, your damping coefficient C, and stiffness, which is given as K. So those are the three variables here. Your electromagnetic force waves, they go through and they excite the mechanical system. They generate vibration, and then the amplitude of vibration is a function of magnitude and frequency of these forces. So in the surrogate model idea that we're talking about, we are creating a behavioral model instead of actually using FEA. Why? Because FEA tends to be time consuming. If we have a model of FEA that can be done really quickly and it can solve in a matter of minutes, iterative might still have a way, but you are now trying to couple every one of them. Lots of software companies are trying to work through that as well. What we are doing is, instead of creating a software, we are creating the framework and we're creating the analytical methods, so you have full control and full information about how that machine design has been evolved. So the structure here basically is assumed to be linear. It is assumed to be time invariant, which means it does not change over time. You do a modal analysis to get the homogeneous problem. You do harmonic analysis to do non-homogeneous problem. And it also determines the response of the structure for a steady state sinusoidal harmonic. And the structural displacement basically are considered to be very small. So the idea of the vibration surrogate model that we have really here is specifically, it combines the accuracy of numerical models with the efficiency of analytical models. So we're not trying to say one is worse or better than the other. Quite the opposite. Like we did for field reconstruction, we used FEA and combined that with polytonic modeling. What we're doing now is we are combining numerical modeling or analytical modeling with FEA. What we're trying to kind of communicate as a philosophy is resources and solution methods are available, so we should leverage them. I would not go as far as saying one is not good enough, because they all have value. The question is, can you add two of them together to create a product that is greater than sum of the parts? Okay, so the accuracy of the noise models gives you FEA-based identification, and the time-efficient approach comes from the surrogate model. You might remember this from the example this morning. I was talking to you about the permanent magnet and how you can combine them with currents, specifically to or the field distribution for field reconstruction method. And we had said that we could actually use superposition to create the method. A very simple idea, a very similar idea, in which you can actually do a model identification based on the deformation response. You get an impulse response from the system, and you get the force applied to each stator tooth. Each one of them will give you a specific response, and you have n deformation responses. Combine all of them, and that gives you the overall structural response for your system. So the identification procedure is kind of divided into 3 steps. The first one, you select the dimensions and the range of and the number of steps. You have to define how much you consider to be reasonably adequate. So the step size you have to see as well, because that will tell you what granularity you're going to get. You get an impulse response for a number of geometries for all the stator teeth. So you actually apply an impulse response, get the figure, and you store that as data. And then you extract the modal parameters. So your modal parameters would be considered to have a good fitting if you have good, and that will give you good model accuracy. If you have an observable trend, that allows you to get interpolation. And if you have it robust, you will need people to touch it the least, right? So the goal really is we're trying to identify what it is we're trying to do. We're trying to make sure we define our metrics for success. We want to have a good fit. We want to have a trend that is clearly observable, and we want to have a system that is robust. If we change it, people don't have to touch it. So this was the system setup that we had here. We had a test lab with a setup that was defined by LMS. We had 2 accelerometers, and then we had 21 locations. We basically roved and got the frequency responses, and we did an impact hammer testing with it. So what we saw basically was that in terms of FEA and experimental, we got a reasonable response. Like I said, you will notice that we actually have to make sure that the frame is tethered at the right point. You have to make sure they are actually tied to the right place for your FEA. So this is the implementation for the surrogate model. We essentially had the electromagnetic model. You had the structural model. They both feed into the system specifically, and they give you the structural model. Yeah. So essentially, in this model that you're seeing here, you get a unitary impulse response for any geometry within the identified range. The idea basically is you don't simulate it for every point. You simulate it enough to train it across an entire range. And once you have that, you are able to interpolate, even if that number was not analyzed in your training data. Now you have a bunch of iterations. So now, just like you said, by having known information about how the system responds for certain conditions, you're able to interpolate what happens if I change something in between. And you can also cause a change in multiple variables, because you know how they superimpose, you know how they respond to each other. So after that, you basically would do reconstruct the deformation response like we talked about before, and that is what is used to identify the system. So when you look at this, like I had said before as well, we need to know whether or not our system was successful. So this is basically, we defined a figure of merit called K control, and the idea basically is we looked at different values for NT and NO. That's the number of teeth and the number of designs in optimization. So we looked at that, and we identified NI, which is essentially the number of simulations. We identified that to be 75. So once again, it's a large number when you're talking about it, but the idea here basically is that it allows you complete design flexibility in the entire design geometry. So we define multiple frequencies, multiple shapes, or multiple components of the stator that we wanted to optimize it for. You see here, the actual and surrogate model actually have a very good fit. So if you take this one step further, now you have what you need there, and now you're going back to incorporating this into your current model. That's the third component. So it requires you to be able to calculate the analytical calculation for acoustic noise. We have another project going on right now in which we are trying to calculate acoustic noise by a different method, but the idea, the framework still remains the same. So you have a reference speed, you have geometry goes into current profiling, natural frequency calculation, acoustic noise. Very simple idea if you think about it. You can define your geometry of your motor to be like a shell. So what you have here basically is the shell here is considered to be an infinite shell. And the reason for that really is because in our case, the only points of interest that we have are the circumferential modes of the stator. Okay, so which means that the forces of the order R that's given in this equation are only going to excite the mode that has this exact same order. So when you have a frequency excitation that is close to the natural frequency, your vibration frequency will reach the reach a maximum, and your excitation will then be observed. So so in terms of the design itself, what you're getting here essentially is you have two functions here. You have Jm and Ym. The J is basically Jm and m+1 are Bessel functions, and then Ym and m+1 are Neumann functions or Neumann functions of this order. So this allows us to describe the overall motor as a shell. One thing to keep in mind here is that it does not include the frame effects. So if you're designing a frame and you're trying to optimize the frame, which is important for acoustic noise, that changes the order of complexity of the problem, because now you're talking about fins, you're talking about the structure, the weight, the material of the frame. That will be much more different. So what we can do is here, the way we have done it, we defined a baseline, and then we talked about reducing the motor acoustic noise. This works if you have a frameless design. If you have a design with a frame, you do have to consider. The switch reluctance motor we had in the lab only had end caps. It did not have any frame, or basically did not have a housing on it. Okay, so this is the time efficient model that you have, and so in this case, what you're seeing here is when the wave number that you have in the direction, the circumference is greater than the axial direction, then the acoustic behavior of a cylindrical shell is primarily going to be circumferential. So it will be defined specifically by the wave number. And in that case, essentially the length of your cylindrical shell that you had is no longer going to be important. I've defined a lot of equations here. I'm not expecting all of you to follow this, but once again, we have published some of this work before. I'm more than happy to share some of this report or the paper if you want to see more of what we have done. This takes it to a whole nother level of calculation, but in reality, all we have done is we have combined the previous steps and created an overall model that takes it from the 2D FEA model, the structural model, and combines that to create an FEA model. So, so here in basically what we also observed is that since your machine geometry is basically the same, what's natural is that your resonance modes are going to be the same because the geometry didn't change. We were trying to see what happens when you operate them at different speeds. What happens at different speeds? You get different frequencies of excitation. So your electrical frequency is changing, but the resonant frequency of the actual geometry is still the same, right? So your FEA essentially tends to, what we did in our calculations, we found out that FEA tends to overestimate what the numbers were. Analytical values in our mind were a little closer to the, in this case, actually it was a little different, but our analytical model and the FEA model were relatively close in our design. And this is basically is the measure FEA model and the analytical model that we had designed for the system. So if you use this information specifically to create a method that allows you to change, this is for a switch reluctance machine, and we were trying to define the optimal control conduction angle. So we wanted to define how we can turn on and turn off a phase. We wanted to do phase advancing, and we were incorporating all of this back into the acoustic noise behavior. Because if you do FEA, you are usually applying a current to the motor, seeing the response. What we were trying to do is we wanted to apply the current, see the response, feed the information back and make geometrical changes, apply the current. So we wanted the entire system to be an automated process. All this time also combining it with electromagnetic. What we, like I said, what we haven't done yet is the thermal coupling, which we are in the process of working as well. So the current shaping is a simple idea. Electromagnetic goes all the way, You optimize it, you add a phase, basically a delta to it, change the current a little bit and feed it right back, and then go for the next position and close the loop for that as well. So each position, we're trying to identify how this system behavior is changing when it comes to acoustic noise. This is basically the optimization when we did the sound pressure level calculation before and after optimization. So before optimization, our modes basically were much higher. You can see that after optimization, the sound pressure level. This is, by the way, is a normalized value. We did a lot of this work that we're talking about here with industry, so we cannot share the real data. We can only talk about it in terms of normalized quantities. So the current optimization, once again, if we do a further analysis and we talk about firing angle change, you can see that before and after optimization, if you change the firing angle along with it, now we are talking about optimizing multiple variables at the same time. You're doing current shaping and you're talking about turning them on and off at a different time. So the benefit is that you get additional degrees of freedom in this entire process by allowing your analytical behavior to have dependencies on specific variables of interest. By eliminating them or by zeroing them out and creating a superposition, you are able to kind of look at the individual responses and then combine them to identify the overall behavior of the system. This is basically the phase advancing methods. As you can see, the analytical method and FEA and experimental were relatively close, and we actually were able to stay very, very close to the numbers. So based on this, I just want to kind of, like I said, this was an opening to talk a little bit about a coupled framework, specifically where you combine different modes of operation. We have so far done electromagnetics. We are doing acoustic noise. We have also done some acoustic noise and vibration before. We're also working on thermal behavior as well. But my vision or my hope is that we start looking at them not as isolated pieces, but as part of a much larger fluidic problem. So on that note, guys, I have a couple of questions I want to just kind of toss in there in terms of trade-offs between accuracy and flexibility, because we talked about right now, if I have existing data, how can I use it? Right? That's a very good question that you want to make sure you adequately define in your system. Like how can that information be used if you have motors that have had previous data? Also, if you have an extra degree of freedom in the optimization, in that case, can this information be used in the design and in selection of components for your drive? Because you're not only talking about the motor, you're talking about possibly controlling the current, where you might want to see a current waveform that is very sharp. You don't want them to be a simple, for SRM, you're looking at a current profile that has reasonably effective shape. What if you had a shape which has a U shape or something different that is very unique? Does your DSP have the right switching frequency capability? Does your sensor feedback give you the right sampling time? Do you have the right bandwidth? So those questions need to be addressed whenever you are talking about designing a closed form solution. You cannot assume that a DSP 2407, the DSP 2407 is going to be effective. You might go to 2812, it's still not effective. And then you go to 28335, you have 28377. All of these are TI DSPs, where you go from being a motor specific DSP to a dual core DSP, right? Now you have more ability to run the system. But what if you are designing it for a system that doesn't have that cost, that space available to put more money into it? How do you accommodate for a hardware-based system, an analog system? Do you have the bandwidth to accomplish something like that? So that's kind of, like I said, this is a big vision at this point that I have, and I'm hoping over the next few years I'll be doing a whole lot more in this space. But there is a lot of work to be done. I mean, from my team, from my group, we're not even close to being done with where we want to be. So I'm hoping that this kind of gets you some ideas, but I wanted to hear if you had any experiences based on your work where you think that optimizing or combining multiple objective functions, or the design of your converter in relation to the machine design, if that is a value even, or do you think no, linear method works? Any thoughts? FEA. Yes, correct. It's a behavior model. That's correct.
If I want to know any value between the two test results, so what will be the coefficient of prognosis? how would you decide that will be
So you are training your system. So there's no coefficient that is defined for any geometry. So you're basically creating those fitting functions. We actually have fitting functions that we define in our paper. We've had a few papers we've published on this topic. I don't know if I have them here. Yeah, I don't include them. I actually had them in the previous slides. So we've published a couple of papers on this topic in the transaction transportation electrification. You can take a look at that. But those fitting functions actually define specific to the geometry. So you need to find the coefficients that allow you to train the system to recognize changes in the geometry, because you might be changing more than one geometry. And the beauty of this is once we have run all of the simulations, each one of the variables can be changed, and you can look at the overall impact without running FE again. So it's not a real, there's not a fixed number. Every geometry will have a coefficient that is unique to it, but meaning the starting geometry. Did that make sense at all, or kind of?
there will be some coefficient called the coefficient of prognosis.
Okay.
If that value will be above 0.9, that will be a reliable result when we are reading from a meta model. But if it is less than 0.9, that may not be reliable. What my question is, how will you make sure that whatever the intermittent results they are reliable?
So I don't think we did the coefficient of prognostics. We did not do that. So I don't have a good answer to give you to make sure the fitted function was good. Most of what we did was a DOE, which was a design of experiments that we analyzed for a given motor. We did this testing and the solution for it. So at this point right now, it was a DOE. So it has not been, I don't think we are at the maturity level, at least this project was not at the maturity level, but we have a good number to give you on the coefficients for that specific metric. So I don't know if I unfortunately don't have a better answer than that at this point.
We are also working in this.
I'd be very interested in talking to you offline, and I'd be more than happy to talk to you if there's any ways that we can share information with you or collaborate. I'd be more than happy to talk as well. So, of course. Any other questions? If not, thank you very much, folks. I know I went over by about 10 minutes or so, but thank you very much. I will see you all tomorrow. Dr. Raghavan is going to be here. So you guys will all be here as well. So tomorrow morning, we'll talk more about AC machine. Yes, yes.
Sir, in case of the SLM electrification, so what is the torque before? So what is it produced by the motor?
So that's a very open-ended question. The reason I say that is because the torque ripple is a function of everything from phase advancing to current shaping, right? So you have to define it more for a point. So our goal was to optimize the torque ripple within a given range, within a given band. You have to define based on the geometry how low or how high you need it to be. So in our case, I have to go back to see exactly what the best case was. So we can give you the best case torque ripple, or we can give you the worst case torque ripple. But there is no one number necessarily that I can tell you that the average torque ripple was this, because it depends on the operating. Like I said, the torque speed curve, you're operating at a specific point, and each one of them has specific constraints that go with it. So I would hesitate to give you a number that tells you that my torque ripple was within 15% or something, just because I don't know that I can tell you that without knowing what the operating point is. Does that help at all? Excellent. Thank you very much, everybody. I look forward to seeing you all tomorrow. But in the meanwhile, please don't go away. Dr. Raghavan and Dr. Naveen are going to be here, so they'll be talking to you guys. Thank you. Taking a break now, or are you taking a break?
5 minutes.
So you're taking a 5-minute break. This is an FYI.
No.
Just had a question when you discussed about noise vibration. So to reduce the stock total, there is some decentering these magnets. That is
Yeah.
one method.
Yes.
So is that adopted for SPM, IPM for all machines?
So mostly for SPM, IPM it can be challenging.
Decentering means how does it differ from staggering? What is that decentering?
So decentering basically means, so staggering is very similar to the idea of staggering. So basically, you are changing the center of the permanent magnet itself. So it's very similar, but if you are doing an IPM, you are essentially changing, you're skewing the center of the magnet rather than staggering because it's one single piece. So it's fine. So for IPM, it can be a little challenging in general to do a rotor skew. So that was one of the methods that I had to find the right reference for you, but that was actually one of the methods that was published in one of the papers. So we haven't done the decentering of the motor itself, but that's a method that was in the paper.
So these things, does it affect the, what is that, field distribution in the air gap? Does it bring asymmetry in the air gap distribution?
Asymmetry,
This
no.
magnetic
Over
field
one,
distribution.
right, over one pole pitch, it shouldn't.
Okay.
So if you're talking about like, it depends. I mean, if you look at every single slot, yes. But if you're talking about if you cover one full pole pitch or magnetic pole, in that case, it should be reproducible. So there will be a change, but it would not be asymmetry. So it would be definitely would be deformed, or it would basically, the shape would be changed more than it was previously, but it should not be.
Asymmetry means like over the complete circumference, can there be a magnetic field distribution that it doesn't repeat?
It shouldn't. It shouldn't. Over one pole, it shouldn't. Once again, I don't know if there's a specific reason why you feel it must, or it might. But if you have the, unless you are actually changing and unless your design itself is asymmetrical, your field distribution should be consistent. So we are actually working right now on specifically looking at.
Together with the stator excitation and the magnets together, if we see, can it cause asymmetry?
In which method are we talking about? The last part or the field reconstruction part this morning?
In the rotor, the magnets, the alignment, if you try to modify.
Right.
So can that cause asymmetry in the field distribution?
No, like I said, I don't think it should. So I would not use the word asymmetry. It will definitely cause a change in the field distribution, but it should still not cause, because you're changing every single magnet, you're not changing just one. Right? So if you change only one, absolutely you're going to get asymmetry. But if you change all of them, then they should all be symmetrical in the same way. They will have the same interaction. So they'll be over the entire, they will repeat themselves. When you say asymmetry with respect to what? Like when you say, I guess actually that should have been my first question.
I've seen us in some machines over the complete circumference, the air gap field distribution
First time. No, no. Right side. Just let me complete this. Video PDF or this mode. So third one, third. Display height present. What is the height? Okay, it comes next slide.
Shall we start? Good evening. We have with us Dr. Naveen Kumar Endla, who is a postdoctoral fellow at IIT Bombay. He did BTech in IIT Gandhinagar. Just after BTech in IIT Gandhinagar, he did PhD at IIT Gandhinagar. So after that, he joined IIT Bombay, and right now he's a postdoctoral fellow, and he is dealing with many projects. So I thought he will give good inputs on this topic. Okay, thank you.
Is this height okay? Fine. Good afternoon. Thank you, Professor Raghavan, for that kind introduction. So I've been working on machine design projects for last 3 years. So I can, if you have any doubts related to simulations or analysis, mainly focused on field distributions and induced voltage, etc., that we can see tomorrow. Today's topic is about how do you perceive the forces that come out of magnetic fields. So I'm assuming most of you have been introduced to one type of understanding or one method of understanding magnetic fields, electromagnetic forces that come because of electromagnetic interactions between two sources. I'll introduce you one more method that I believe gives a slightly deeper insight into what happens inside the air gap of machines. But I'll stick to simple examples. But towards the end, I hope you will be able to extend the idea that we have seen it, through the presentation, and accept that that is also true for machines, right? So it is very interesting how the field of electromagnetics has evolved. Like, they have the earlier scientists and people who have discovered the initial experiences with magnetic fields, what they have observed, and finally where we are. Everything is based on experiences, experiments, and how do we combine all these experiments, etc., into one form of combined mathematics, which was done by Maxwell. So in a similar way, we'll also try to, this presentation is also set in some approach where I'll show you some examples to tell how fields interact, two different sources interact, and how are the forces transferred. And then finally, we'll see its math, right? So the first recording of magnetic field behavior is they found a mineral called lodestone, and they have found that it can attract another piece of the same material, or it can also repel that. Similarly, it attracts a piece of iron. So that was the first recorded behavior. And then William Gilbert has established that Earth itself can be considered as as having a weak electromagnetic field, right? And then Charles Coulomb has established that two magnetic charges, the force between these two charges is inversely proportional to the distance, the inverse square law. This is a simple history I'm taking you through, right? And then Oersted has established that if you put a magnetic needle around a current carrying conductor, it gets deflected. So he was the person who established that the magnetic field circulates. So with that help of that compass, needle compass, he has established. And then next set of experiments and observations were related to two parallel current carrying conductors. They found that when they are brought to each other, close to each other, they are repelling. If the currents have the opposite polarity, they are attracting each other. Ampere was also the person who proposed the first mathematics that has given some structure to forces due to magnetic fields. So, and then the main set of experiments or observations where we started thinking that somehow electricity and magnetism are related are to be credited to Michael Faraday. So this you all can I'll not take you through all these three. You can there are more interesting animation based illustrations of these three devices. So but what I'm wanted to say is he's the person who said that who introduced the concepts of induced voltages and introduced some devices that can demonstrate electromagnetic rotation, right? So after his set of publications, and sometime I think Maxwell has proposed that both electric and magnetic field are some subcomponents of some fundamental force, and he gave his set of equations that have finally brought us to the state where we understand the electrodynamics now, right? So just quickly we'll go through these equations. That the first one says the electric field emerges out of a point charge, right? Or if you have a distribution of electric charge, then it has a different emergence, but more or less the property or the phenomenon of electric charge coming out of electric field coming out of a distribution can be described using this first equation. So it doesn't get reflected there. Okay. Okay. So the second equation says the divergence of magnetic field is 0. I assume that all of you are familiar with it, so I'll quickly go through it. And the third is if there is a changing magnetic field and there is an induced voltage, the induced voltage gets developed in a way such that if you allow some currents produced because of that induced voltage, they'll oppose the source that is causing it, which is the change in magnetic field. And the fourth equation says if there is, for a moment, let's put this aside. We'll first understand what is the del cross B is equal to mu naught into J. If there is a current carrying conductor, there is a curling magnetic field around it. And the third part says magnetic field can also be produced by a changing electric field, right? You need not have a distribution of current or electrons moving. You can also have an electric field propagating that can also produce a curling electric field, a curling electric wave around that changing magnetic field. Like simple interpretations of these equations, right? So these are the fundamental equations that were proposed, let's say, a century ago, right? But when we come to machines, what we present, so the methods, the three methods I'm going to explain to you, or we are going to see what is the need of these three. We have a lot of literature on machines, right? But why do we need to understand these three methods than what we conventionally use, right? The concepts and the formulae of classical electric machine design and analysis are using the integral form of Maxwell equations. So we have seen the differential forms. So they are, for example, let's see this. This is integral of B dot ds is equal to 0. That is, field doesn't come out of a surface, right? Integral of E dot dl is equal to minus dou B by dou T into ds. That is, if you have a surface, the flux changing in that surface is equal to integrate the induced voltage in a loop. You will have the same, I mean, you will have the LHS and right hand sides, LHS and RHS same, right? So these kind of integral forms of these differential forms applied to highly simplified and symmetric systems to bring out some set of principles or equations which help us in design analysis, right? So if you use this simplified set of equations as a basis to for electromagnetic energy conversion, so again, these simplified expressions are essential, because without which you will not be able to derive useful models to either control or design or do some engineering analysis. Like, for example, you would like to understand what happens to inductance as you increase the machine diameter. What happens to the back EMF if you are increasing the speed? You don't want to sit and analyze Maxwell equations or think from the perspective of Maxwell equations what's happening. You want to derive some equations that are handy and use them. So there is significance, there is important, and the simplified expressions have meaning. But sometimes when we do not go back to the Maxwell equations and see some of the phenomenon in detail and use the simplified equations, we might misinterpret some aspects of electromagnetic energy conversion, right? So yeah, I think I covered this point. So we will look at the force concept here out of several other topics. What did Maxwell say about force, electromagnetic force, and what are the three methods that we can use to understand the forces emerging out of the electromagnetic fields, right? So here it starts, the first example. So now consider that you have not seen many methods. Like, let's just start with this example. So there is the first figure on the left hand side is the field of a conductor. The conductor is into the screen, and it And then the second figure is a uniform field, right? You agree with me? Without, let's say, using what you by how to get the force on the conductor, is it possible to guess what is the force on the conductor just by looking at this pattern? Can someone answer this question? Like, let's not use any math. We'll just have a look at the resultant field and say what is probably happening to the conductor. Is it? Yes, it is downwards. How did you answer that question? I mean, what is the basis?
By just looking at
I'll
the
come.
without applying any law, so I saw those are like elastic bands trying to push.
Yes, right. Same. Yeah. I think even the title has some hint there.
Actually, whatever they speak, it won't be there. So
Okay.
please repeat it, because only your mic is connected with that.
Yes. So the audience have answered just by looking at the figures. Looking at the figure, because of the pattern, we can consider them as some kind of stretched strings in some elastic state. So they are pushing the material volume at the center in the minus y direction, right? So this is what we take from this first example. Magnetic fields can be considered as elastic strings. Maxwell called them as tubes in some stressed state, right? The pattern of the lines and the associated stress reflects the resultant forces, right? So if there are two sources of magnetic fields, it's like more formalized statement. The direction of force acting between them can be predicted from the pattern of the resultant fields. Even the subcomponents, like if there is fx, fy, fz of this force, you can extract it. So if we are using the stress-based approach, like you are saying that there is some kind of stress in the magnetic fields, this I'm calling it as method 1. We'll see what is method 1, what is its name as we go further into the presentation. Yeah. Yeah. Okay. This is a second example. On the left hand side, there are two conductors carrying the current into the page, and it is summed up with a uniform field. Let's talk about the third figure, resultant field. What can you say about the two conductors? If I leave them like that, do they get pushed into each other or pulled into each other? Can you be, yeah. Okay, think again. Is there a different answer? Okay, anyone else? Any other answer?
Do you expect them to tell based on that field distribution or based on what they are studying?
Okay, you said based on what? Using what you have learned earlier. So I think, no, based on, they should attract each other, right? Maybe we did some sign mistake, probably. Check it again. So, okay, let's get back to this figure. Let's get back to the left-hand side figure. What does it say? What happens to the conductors? That's the resultant field of the two conductors. Two conductors carrying current. First figure. As you said, they attract into each other. Right? We'll go ahead. Now, does that aspect is it getting reflected in this figure? That those two conductors are feeling some force into this one in minus x and this in x. No, treat them as some strings, as we have discussed in the last. Like if a string is stretched.
So that screen.
I'm trying to go back.
Next.
So is there a force in this direction? I'll stay. Okay, sorry. In this direction? Yeah, there is a force in this direction. There is also a force in this direction. Do you agree on each? Yes. The pattern says these two material volumes try to come closer. At the same time, they'll also be pushed downwards. Right? So the initial thing that the conductors, because they are carrying parallel same direction current, they should get into come closer. And in addition, if you treat both of them as a single conductor, like two conductors placed side by side in a uniform field, they should feel a force in the negative direction. That is also getting reflected, right? So just another example. Third case. What does the figure say? The rightmost resultant field. Okay, the left hand side figure says they repel each other. Is that clear that there is a repulsion force between them?
Yes.
Everybody agrees? Okay. If anyone has a doubt, you can think about on the left hand side, the first figure as there is a straight line in between, and there are some circles that are pushed onto that wall, and they're trying to come out. In that way, you can perceive that and say these two conductors want to move away from each other. Right now, that kind of coil system or conductor pair is kept in a uniform field. So this is the resultant field. So what kind of forces are you able to see here?
Actually, very simple. I think these two are, if we are combining, then this will come.
Yes.
Because it's a very simple. We can add a factor.
Yes.
There is some force line, and its nature is like that. Then it will try to connect in that way, whatever they are coming, and they opposite side have adding because they are same natures. So that way we can get this kind of pattern.
Yes. So I'll rephrase what you said. So we can apply superposition. That's what you're saying.
Yeah.
Yes. I simply did superposition to get this figure. So there are two aspects. Like if you remember the earlier examples, the cross conductor should feel the force in the negative direction. The dot conductor should be feeling a force in the upward direction. That is being reflected. And these two should be moving away. If you treat them as these two material volumes as two different systems, right? Like there is this stress in this direction and that, sorry, force. Yes.
Cancelling. That's why there is an absence of flux like.
Yes. Yes.
And the other one is just adding. That's why it is strong. So both flux lines there.
Yes, you're making an additional observation, or let's say you're explaining why the flux lines are in that direction, in that way.
How can I say this? So, like the other previous case, it is giving a force down. But here it is not clear.
Yeah.
One is reducing the flux lines, other one is increasing the flux lines.
Yes. So that you gave the reason. I'm asking, see the pattern, accepting this as the final pattern. You gave a. Sorry, sir. Did I make any mistake?
Actually, one thing I'm realizing now, sir, natural phenomena. If you are going to put this is a uniform magnetic field we have, and if you are going to do conducting wire opposite directions, you are not looking at it that way. There is so many reasons. That's why it is going in that way. Because you have already told that elastic strain. So if you are going to think in that way, then we are getting that will arrange in that fashion. So whatever you are explaining.
See, actually, probably what you are asking is in what direction the force will be, right?
No pattern.
Yeah,
I think
okay.
pattern adding of this.
By looking at the resultant field distribution.
But there are two sub forces, sub questions, sir. One is what each conductor is feeling and what each conductor as a system is feeling.
So force will be something like minus 45 degrees, something like
Uh,
this will be minus 45 and that will something like
They want to repel each other and they are going at an angle like this. That is what we can understand, because one is going according to this magnetic field, it should go downwards. According to their own magnetic fields, they should go separate.
yes.
So when you add them together, the resultant is they have to move diagonally like opposite to each other. And according to that field lines, that elastic things also pushes them in that direction. That is what I understand.
Yes, yes. I think more or less all of you have understood what answers I'm expecting. You are giving correct answers. So, but let me also just rephrase those answers. So, if you treat these two as separate conductors, as you said, they have some forces going in, let's say 45, assuming that the forces are similar, right? If you treat this as a system, like you bind them with a rod, some non-affecting rod, then it is feeling a torque, right? So yeah, that last one I just wanted to add in addition to what you are saying. So yeah, so the torque, if you assign a vector to it, it is along minus z hat into the page. Finally, one more example, that is, we just looked at an example that kind of brought us close to machines. There is a field and there is a coil, it is feeling a torque. Again, we also say in machines that things have two fields have to be orthogonal. If I try to show a similar example, try to show resultant fields in such case in a linear or let's say in a developed coil, you'll see that the resultant fields are in the video. My hand won't come. Resultant fields show that they want to slide into each other, right? It's like a the bottom coil is like one north-south magnet, the top coil is another north-south magnet. If you see the resultant fields, the magnets want to slide into each other, right? If you don't let them slide and just keep moving, then that force is maintained. This is what happens inside machines. You maintain orthogonal 90 degrees, electrical 90 degrees between the stator field and the rotor field, and you keep rotating the stator field to get the torque. There are different versions of implementing it, and we have different classes of machines, but essentially these kind of fields and their stresses create torque inside the machine. So this is all about the method one in terms of observing the resultant field and probably predicting what is happening inside. Right? But an important thing here is if the pattern is perceivable and you can say something out of it, that's mostly true. Right? It's not like you don't guess either bhi ho sakta hai, udhar bhi ho sakta hai. If pattern is clearly saying this is the direction of force, then math also will give you that answer. But what is the complexity in machines is because of very small air gap, you won't be able to see this kind of clear patterns. But the phenomenon is applicable. That from the resultant stresses, you can get the forces, and somehow, if you look into those math, you'll also understand many other accepted principles of machine design or control, why it has to be so. Okay. In the second method, that is first method, we will look into its math a little bit later. So let me take you through the method 2, where we treat one field source as a magnetic charge. We are not interested in what is the magnetic field distribution of that source. Like you have two sources, like in the earlier case, I have a uniform field and I have a conductor. If I say the conductor is not a field source and I want to treat it as some magnetic charge, like an electric charge, then in that method of estimating force, if you are using such method of estimating forces, that is method 2. Like solve for the field distribution of only one source, considering all other things in that surroundings, whereas the other source, you represent it as a magnetic charge, right? So how do you represent it? That's a different thing. But the essence of this method is you only consider one field source. The other is simply a charge. So you know this formula B can apply in that method. It is ideal cross BE. BE is a vector here. So you'll have the boldface BE is the vector. The normal BE is its scalar value, right? So that's the Lorentz force method. That's method 2. One important thing here is if you are implementing this method, you need the field of the source which you are solving exactly at the point where your magnetic charge is present. Like if you are applying BIL here, you need to know wherever that conductor is, what is the external field's value at that point. You can't take some other point's value and apply it. If somehow that is not solvable, like you in your problem domain, you're unable to solve the external field at the point where the conductor is present, then it is also allowed, or it is also possible to represent that magnetic charge equivalently at a place where you have solved the magnetic field, right? I'm sure you want to look at an example where this kind of, like for example, see in machines, I think you'll know that the magnetic field takes the shortest path to the ferromagnetic material. So if the permanent magnetic field is coming out of the rotor, it doesn't reach the conductors, right? It takes the shortest path to the teeth and circulates. So there is no magnetic field in the slots. Is that okay? Is that statement? If you embed the conductors into the slots, and if they are slightly away from the air gap, there is no field at the conductors. So in that case, it is okay if you bring this eye. How far should I stay away?
Don't touch the screen.
I didn't touch. I think go. This will also. You can say that this cross is present just below the stator, and you know the B value there, and apply BIL and get the system level forces and say this is the torque. That is also acceptable. We'll see an example why this will also work when you don't know the magnetic field at the point where the conductor is placed. The last method, method 3, is again explaining using the same example. It involves some kind of virtual displacement and energy estimation, right? What we do is mathematically we say that the object of interest, let's say here it is the conductor, has moved in the direction y. Let me take it as an example in a differential movement, right? So I'll explain some more details here. So what is the change in energy when that object has moved by that small differential distance? Use that energy and estimate the force. Like force is change in energy by the displacement, right? So this is the third method. We have seen 3 methods. One is stress based, the other is magnetic charge based, third one is energy based. So here it is the conductor. Like if you want the force in the x direction, move your conductor in the differential for a differential displacement in the x, or if you want in z, move it in z direction. And between these two new positions, what is the change in energy? Is that clear? So stress, charge, and energy, 3 methods. So if you have an analytical expression for the magnetic field distribution, then you will simply differentiate the energy with respect to, let's say, a rotor movement or the conductor movement. If it's a finite element analysis solution, you assume that the meshes got deformed by a small distance, like all the triangles inside the air gap got stretched by a little displacement. And because of that stretch in all the triangles, what is your new solution for the magnetic fields? You see what is the change in energy and take the differential, then you get all whatever I said is is presented in a simplified matrix form by researchers. So it can be doable. Like, though even I'm just saying in statements like the meshes got deformed and there is a change in energy, everything can be like easily implemented in a computer, right? So I'll take you through one example and we'll see what is the concept that I'm trying to convey here. So let's go back to the method one. We are trying to understand what is electromagnetic stress and how do you compute forces from it. Professor Mahesh has introduced it for a machines. Like, so we will apply this for that simple example that I showed. So it is a state of electromagnetic fields. That's what Maxwell has to. It's a state of that tubes is the stress. The values of stress is dependent on the orientation and the strength of the field. From the stress at each point, the force acting can be estimated using methods similar to how you estimate mechanical force from mechanical stress. Have a stress in this direction, multiply by that area, that is the force in that direction. Have a stress in this direction, multiply by that area, you have the force in differential force in that direction. Same approach is applicable, but their theoretical properties are not same. Units are same. The way you extract forces from the stresses are same, but their properties, let's say in terms of continuity, where they're present, where they're not present in a material, they are not same. Yeah. The forces or energy transfer, anything that is happening out of a volume can be computed using these stresses. So before we get into the math of this, let me quickly introduce you to the coordinate system that we are going to use. Generally, X, Y, Z is used in other domains, but in machines, we have planar magnetic fields, right? So it is easy to represent them in cylindrical coordinate system. So we will be considering a right-handed cylindrical coordinate system. That means the vectors in this coordinate system can be shown using your 3 fingers of the right hand. Right? The r cross theta is z hat. I mean, if you do curl, and you can use your right hand to get the output. This is very convenient if you have a planar magnetic field distributions, right? And they are aligned to radial and tangential. There are radial and tangential components in your field distribution. Any questions in the earlier slide? Okay. So the
Stress calculation, force calculation, you are doing from the magnetic field as well as the current carrying electric. You can see that 2 MMF that are the 2 MMF source, those are present in the machine. So what's the difference? Like machine calculating the stress and utilizing then the area we can go to force.
So you're asking, so the question is, what is the difference between MMF based method and stress based method? Is that or okay question? So the MMF based method that BI, the field, from there you can derive what is the flux magnetic charge based method. So there, if you see, find MMF on both sides, for having both fluxes in the right hand side of torque. I would say that is magnetic charge based method. Applying, we're not using the distribution, the torque value. Set. Okay, did that answer your question? So, do you want to add something? Oh, it looks I am odd. Now, one more thing is all of these three are fundamentally, I mean, you can say that, like, if see, these are theories, these are three different methods, they should all lead to same answers, right? So you can, in an abstract sense, you can use this, you can start with Maxwell stress tensor and do some curl, divergence, substitutions, and come to magnetic charge based methods, and do some more substitutions and show that the energy based method also gives the same answer. What is the difference is how you implement it. We are at the implementation stage. At the abstract theory, everything is same, right? I'm looking these three methods at the implementation, in the implementation layer. Okay. So we'll be doing this approach on this example. We need to take a contour around the object of interest, compute the electromagnetic stress on that contour. So this contour can be anywhere. It needs not be at certain distance or somewhere. It only thing is it should not intersect the two sources, right? Find out the electromagnetic stress. I'll take you through these steps with the help of the math. So let's first find out what is the, let's first look at what is the field of the conductor. The field of the conductor is, I think you all can derive, it's a uniform, it's a long current carrying conductor into the page. So it is conductor B is given by mu naught I by 2 pi r. It's along the tangential direction at every point, right? I'll go a little bit fast here. Yes, any question? Okay. And I'm representing both of these independent magnetic field distributions, like the conductor's field and the uniform field in cylindrical coordinate system, right? Simple math here, like you have a B in this, you have B external, the showing by red line. It has B sine theta and B cos theta along the normal component and the tangential component. So that vector representation in the cylindrical coordinate system is B cos theta n hat minus sine theta theta hat. Now, in Maxwell stress tensor, if you look at Maxwell stress tensor in cylindrical coordinate system, the normal component is given by 1 by 2 mu naught into Bn square minus Bt square, whereas the tangential component is given by 1 by mu naught into Bn into Bt. It is, I think it is also very intuitive, because what it says is the volume feels a tangential force proportional to how much the string has bent in the tangential direction and what is its strength in the normal direction. Does it make sense? And how much pull it feels in the normal direction is mainly proportional to Bn square. But if it has some bent, that bent is not contributing to the normal force. So some kind of minus Bt square is there, right? So that elastic string concept is also getting reflected in these two equations. Yeah. So once we have these stress values, we go to finding that differential forces on that small volume. So please note that these stress values are at the point you have computed, right? If out of this volume, there is a magnetic field line, the blue color line, it has the Bn and Bt components. So you find out what is Bn square minus Bt square at that point. So that stress is valid at that point. And you get a differential force at that point, a differential force in the normal direction and a differential force in the tangential direction. Once you have those two forces, so they say that so it is these forces are in that two direction, normal and tangential. Now, if on the system, if you are interested to calculate the total force in certain k direction, right? That can be anywhere. Then you take the component of normal force and the tangential differential normal force and tangential force along that k hat. 3 steps. Get the stress values, get the differential force values due to those stress values. That is simply multiply with the differential area, like for example, it is r d theta here in the example that we are going to do, and then multiply with, and then to take the dot product of it in the direction in which you want to find out the total force acting on the system, right? So that the first line is the conductor field, and then the external magnetic field in the cylindrical coordinates, and sum them up. So you have a normal component coming from only the external field. The conductor fields in the resultant field, the conductor's field doesn't contribute to the normal component. So you have only b cos theta in the n hat. Theta hat has both. So substitute that expression here. You have this coming up, and
This will be b sin theta, right?
so which one?
The second term.
Yes, sorry. Should I write on the screen?
Yeah.
Should I write on the
If
screen?
you want, you can write.
Thank you. That's b sin theta. And I'll substitute them into the normal and tangential stress value. The small f is the stress, and then find out what is, okay, in this example, we have already seen based on the resultant pattern that the force is in the negative y direction. So let's find out that. I'll try to find out what is the force in the y direction. So Fn, so you can simply take the components of normal, like you have dfn and dft. What are their forces in the k in the y direction? So you so that's how you can get dfy, the differential force that the volume is experiencing because of the stress at that point in the y direction. It's little bit big, but what happens is when you integrate all these terms from 0 to 2 pi, only those that has sine square theta and cos square theta will remain. I'll share the slides. So this is also some, again, if you see into the expressions, if there is a term that is like be square, that means whether BC is there or not, it will be there. So the external fields by itself cannot apply a force on itself in the y direction. Similarly, there is a term like BC square. So that means it will be there. Like if you come through this approach and suddenly put B is 0, BC will be there. So this term will not be non-zero. So anything that is not mutual, that will sum out to be 0. Right? Why? Because they have something like cos square theta sin theta, or cos square theta sin theta, or sin square theta. I might have missed some things here. You can go back and check. It's a simple substitution. So integral of cos square theta sin theta 0 to 2 pi is 0. These are some, there are some basic, what do you call them, identities, like 0 to 2 pi if cos n theta into cos m theta, if n is not equal to m is 0. Such kind of identity, based on such identities, all these terms will become 0 except the mutual components. You do all this, you'll get the force is BIL. You already know this, that you can also use that magnetic charge method, but we have taken a lengthier path. Let's see what is the use of it. And the method 2 also, like as I just said, you can also apply the method 2. You do method 3 also, you'll get the same answer, provided you have analytical expressions for this example. Right? So we'll go to the example where what is the use of understanding additional methods. So let me take another example. Here in this case, in addition to the uniform magnetic field and the conductor, there is a conducting shell placed around the conductor. Is that clear? There is a conductor, and there is a conducting shield. Both of them are placed in a uniform field. Can you tell me now what is the force on the conductor? One by one. What's your answer? Downwards. What's your answer? Upwards. Any other answers?
One more answer came no force. Because the force will be acting on the sheet.
Okay, this is the third answer. Yes. Okay. So there are three answers. Downwards.
You can give one more option.
Let me think. No force. No force is third option.
No force is third option. One more option you can create so that
So you suggest one more option.
data is not adequate.
Not sufficient. Information is not sufficient. Acha. Another suggestion is the conductor comes out of the pitch. Yeah. So okay. So your third option is correct. There is no force on the conductor, but how did you arrive at that answer?
The same principle that we use for EMI. Consider EMI. We use coils.
Yes. Okay. But EMI, there you are stopping dB by dt, right? There is no dB by dt here. Okay. Okay. But you are right. So let's see from what we have learned so far. How do we say what is the conductor on the what is the force on the conductor, and how did the force, let's say if it got transferred onto the shell, how do we justify that? Yeah. So let's say there is no conductor. First, I have introduced the shell into the uniform field. So what would be the field pattern? How does it get? So this figure doesn't reflect that. So I'm asking, how does this uniform field gets redistributed if you introduce a ferromagnetic shell, ferromagnetic hollow cylinder? No field inside the cylinder.
Yeah. It will take shape like structures, cylinder structures.
Okay. What is your answer?
Same.
Same as this? But
Same
whatever he said. Okay. Yeah. So the audience are saying that the field, at least some field will take the shortest path or the ferromagnetic path as it goes through this space and comes out, right? That's true. And what is the reason that we give for this? What happens if it doesn't take that path? And what is the advantage of, like, what is the difference if it takes this path, like high reluctance path versus low reluctance path? Minimum energy. Yes. So the field, if it were taking the high reluctance path, it has more energy compared to the field, right? It's like half b square by mu naught is the square by mu. The mu is equal to mu r into mu naught. So if the sum of the field takes this path, it's completing its path by having less amount of energy, right? There's some field line there. If it has to come all this way, there is a trade-off. Like it has come this way, and only some path has lost its energy, has minimum energy, but rest of the path has high energy. So only some set of lines will come here. Can I go ahead or back? Okay. but the rest will stay straight, right? Maybe in tomorrow's lecture, I'll give some more justification on this. Like what other, is it coming straight away from the Maxwell equations that the fields take minimum energy path, or is it some other additional equation that this minimum energy concept? But today, let's go ahead accepting that fields take low energy. So as you all said, the fields take the shortest path. So in this left-hand side figure, so there is a red is north. Let's say the field is coming, emerging out of north and going towards the south, and I have introduced the shield. So there is a dot at the center. There is no current in the conductor. So as you all said, the field is taking the path towards the ferromagnetic mill, and then there's straight part. And this part, because when I did the simulation, the north and south magnet is limited to this height. So the fields are circulating here. Right? But if you focus on this area, sorry, if you focus on this area, then as you all accepted just now, the field takes the shortest path and the rest remains the same. And I added the conductor. The earlier pattern is back. Any questions about this? Okay. Now, why do we say the conductor is experiencing no force? Because if you look at, let's see it from two methods. Let's first use the easiest method that we know, which is BIL. If I want to use the BIL, I need to know what is the external field's value at that point, and that B into I into L. So based on this figure, I have a current I here, and in this method, I don't care what is the field coming out of the conductor. I only need the information of the external field. So B into I into L here is 0. There is no, we are seeing the FEA solution, and we also accepted that based on minimum energy path, there is no field here. The other is, so to get this pattern I is 0 here, so to show what happens to external field.
Slide I is there. I was there.
Yes, so that's the whole problem. If you apply Maxwell's stress tensor, you know that the external field is not coming inside. Like if you apply Maxwell's stress tensor somewhere here, don't go out. Use that contour within the shell inside, but around the conductor. The external field is not coming inside. Based on that concept I just said, that self field cannot give put any force on that, right? Like the conductor field itself cannot drive it in any direction. So that is how we say the force on the conductor is 0 using let's say MST or Lorentz. For even energy, you can say that if there is no field, whether you move conductor a little bit up or down, there is no change in energy. Now, how do we say that the force got transferred onto the shell? This is the case where you cannot use Lorentz force as such, but if you want to use, imagine that you have removed it and apply it, and then say whatever force that you got is on the system, not on the conductor. That is how you can apply Lorentz force here. It's an equivalent method. But if you want to go a method that is directly applicable here without making any equivalent representations or using some approximations, apply MST around the shell, right? This is not a different case compared to the example we have done. If you have taken a large distance, I mean, you take the contour at a sufficiently large distance where the fields didn't get disturbed by the shell. We have just seen that at a slightly higher distance, let's say here, the external field is same as earlier, right? Similarly, the conductor field, if I write mu naught I by 2, that integral h dot dl is equal to ni, and take a contour here, the conductor field still remains the same. It is still circulating, and here also you'll be able to solve that the conductor field, just the conductor field, is same as earlier. this shield only improves the field of the conductor in this region, whereas inside the shell and outside the shell, it remains same, whether that shell is there or not. Because integral h dot dl, it didn't get changed. I mean, that you apply here or here, it is that your answer should be same whether the shell is there or not. Any questions on this?
The conductor generates a field. And also, something is there. These two fields are interacting in the ferrite.
Let's talk here. Tell me.
These two fields are interacting. It's ferrite.
Yes,
So
that.
will that create resultant force on the overall cylinder?
Yes. Yes. We're looking at the justifications for that. So my point is this, that the conductor's field here and here remains the same whether the shell is there or not, and the uniform field is same at a some slightly higher distance. So as we have done for the earlier simple example where the shell is not there, we can choose a larger, sufficiently large distance where the uniform field remains same and get the same answer. So our application of Maxwell's stress tensor told whatever is there inside, that is experiencing a force BIL. And in another, just before, we have seen that the conductor has no force. So this is the proof saying that the shell is, this is the justification for the shell is having the force, but not the conductor. Agreed? But we have also seen that I can simply remove the shell and apply BIL and say that the whole system is having BIL as the force. This is what we do in machines. In fact, the field is not reaching the conductors, but we assume, it's clearly mentioned in all the textbooks, that we assume that the conductor distribution is just below the stator surface and apply Lorentz force or BIL or say MMF based methods. So based on what we discussed today, we can say the core material is not just a medium for magnetic field, it is also a medium for forces, like let it be normal force, the radially attracting or deforming force, or the torque producing force. It gets transferred onto the stator surface or the rotor surface if it's an induction motor. If it's a permanent magnet motor and the material, if the rotor core is behind the permanent magnet, that is different because the interaction is happening at the above the permanent magnet. So at least in induction motors, both stator and rotor core have the forces, let it be normal or tangential. Any questions? So in general solvers like finite element analysis, Lorentz force is not used. What is being used is either Maxwell's stress tensor, not exactly the way we have used. There are some improved versions, like an average version on multiple layers. We have applied on a single contour. An improved versions of Maxwell's stress tensor and virtual work method are being used in FEA. Yeah, that ends my presentation. Just gave you an insight into magnetic forces. If you want to read more related and understand more in this area, so some of the references are here. I'll share with you these slides. You can look at them. So magnetically shielded conductors, how much force? Okay, if there is any saturation, then only some force gets transferred onto the shell. Some remains on the conductor. So there are such kind of publications in literature. You just want to read about some simple papers on shielded conductors. They're a little old, somewhere in 1962, etc. And Maxwell stress tensor, you can find a lot of literature starting from 1940s, 50s, and up to 2010s, which explain how to understand it or how to use it in different domains. This 2007 paper, you can read, that is simply applied and explained what will you find if you apply Maxwell stress tensor in machines, right? Virtual work is, I think you might not have accepted it in this with this name, but you might have known this as energy or co-energy based method. It's the same method, but when it is being used in finite element analysis, it's called virtual work method. So some examples you can find in the this Paul Cross, the famous book. If you want to read about FEA based implementation of virtual work, you can read the second reference. And yeah, a course that will help you to do FEA for machines or learn FEA is with, the last one by Professor S.V. Kulkarni, IT Bombay.
Typically, in which semester this course is offered?
So this is now available online for free.
Anytime student.
Yes. Yes. Just type this name, you will get it.
Any registration charge?
No, it's like it's on YouTube.
No, certification.
It's a certificate.
Usually there will be course with exams, etc.
So that might be there. It's like NPTEL has two modes. One is you do it for free. Other is if you want certificate, you pay some money. It might be there for this course. I haven't checked. Should I end this? I have a couple of more slides, but I can do it tomorrow. Yeah, any questions? And then we'll think about next.
I just want to know your point of view. If I use that cylinder as a non-magnetic insulating material.
Oh, let me think. Non-magnetic insulating material for which fields?
For motor, let's say for motor, for shaft.
Okay.
Now, what will be the behavior of the fields inside the rotor?
Okay, you are using a non-magnetic shaft.
And as well as electrically also not magnetic.
Yes, sir.
Both magnetic
So you're
and electric insulation.
Okay. So okay. Does it have any effect on the rotor core field distribution?
Yeah, what will be the effect on the field?
Okay. Do I have any figure? Okay. So let's for a moment assume that this whatever I have shown in this figure, this is the back array that supports the circulating or magnetic field that is closing the path. If you have sufficient width and have non-magnetic material, there is no problem. But if you don't have, then you are forced to use non-magnetic. Otherwise, there is, I mean, you don't want anything like you don't want your shaft to be magnetic, right? For safety or not to induce any additional eddy currents in the bearing, or that will eventually deteriorate your performance. So you have one more question?
Yeah. Instead of that shaft, if I use the insulating material in the slot for the winding and not in current windings, then what will be the behavior of that fields around that winding? That's a for slotless motor. So there is no T. So there is no path for the lines to flow from there.
Okay. If so, the question. Let me rephrase the question. There is no stated T. The windings are placed at some other plastic surface. They are tied to some plastic surface. Non-magnetic. Yeah. So these kind of machines are there. They're called slotless machines. They are being used in very high machines. In that case, yes, the force is on the conductors, but you have to make sure that you have taken care of the adhesion and everything such that the conductors do not move here and there. The field, yeah.
So, but in that case, no lines will be flowing through the cylinder. And nothing
The plastic cylinder?
Yes, no, that is non-magnetic.
No, no.
It will flow
Yeah, complete the question.
from outside that particular cylinder.
Yes.
It will not be flowing from that conductor also.
No, that's not true. So when you add ferromagnetic material, you are helping the magnetic field sources present inside the machine to give out their magnetic field to a greater extent. If you don't do that, there will be still field coming out of these magnetic field sources, but it is not high enough. So whenever you see these slotless machines, they're high speed machines where the B is less. The magnet's B is less. Like if you have this core, you will have an average flux density, say 0.8 in an NDFEB SPM machine or IPM. Whereas if you go into that slotless machine, you'll have 0.2 or 0.3, right? So it's like even a magnet suspended in the air has magnetic field. So you're using that, a field strength that's similar to that to run the machine, to run the motor. So there is a field. It's not that in a slotless case, there is no field. Did I answer your question?
Yes, sir.
Yeah, okay.
But is there any chance that the field will get interacted with the winding? Or
Yeah,
it
that's
will create a hotspot in that winding because of the concentration of the field outside those insulations for each and every conductor.
okay. You're saying, are there additional loss related effects in a slotless case?
Yes.
Yes. I don't know about the insulation part. Is there any issue? Okay. So probably what you're saying, compared to slotted case, in a slotless case, there is more field coming out of the rotor towards the stator. So there is more possibly, you can, this effect, if it's there in your machine, you can call it proximity effect. So if the conductor has a current redistribution, because some other field, not its own field, then we call anything is actually eddy effect, whether it is skin effect or okay. So yeah, there can be more proximity effect, and then the heat loss can be higher. Yes, but I haven't worked on that. I just heard about such machines and know some concepts to understand them, but I haven't personally worked. So yes, possibly there can be more proximity effect in slotless machines. Any other questions? Thank you for this opportunity.